Welcome everybody to my series on probability and statistics. As always, I am Dr. Lathram, and today we'll be talking about expected value in simulations. So let's begin by reviewing some of our theory for probability. And let's start with our axioms. So remember that when we're talking about probability, we start with the notion of experiment, and we talk about the sample space, S, for that experiment. Now the sample space, remember, is just the set of all possible outcomes for the experiment. Then on this sample space, we form an algebra of subsets. And if you want to review what the properties of an algebra are, go back and take a look at some of our previous videos on sample spaces. But we've got an algebra of subsets of S, and the elements of this algebra we'll call events. So if we've got an event A in this experiment, then we will assign a real number to it, and we'll denote it by either prob A, P of A in brackets, P of A with open brackets, and that number, that real number, we'll call the probability of A, and we've got certain axioms that will apply. The first is that for any event A, our probability will always be between 0 and 1 inclusive. The second one is that the probability of our entire sample space has to be 1. And thirdly, that if A and B are mutually exclusive events, so they both can't occur simultaneously, then the probability that A happens or B happens is equal to the probability of A plus the probability of B. So since we're talking about simulations, that means that we're going to be using R. So let's go over and see what some of the commands might be. So let's run some simulations. So let's get R started. So from console window, we'll get R started. Now remember that our axioms for probability, we had that all the probabilities had to be non-negative. So all probabilities had between 0 and 1, and that the probability of the entire sample space was going to be 1. Well, we can start off with any vector in R, and I'm going to call it P, and we denote our vector. So instead of equal signs, we have this arrow assigning operator in R. And if I want to denote a vector, I'll put that in open brackets with this C on the outside of it to know that I'm talking about a vector. So if I just make up some numbers, so let's say that I have some numbers, how about 5, 3, 9, all separated with commas, 12, 25, 82, 97, 17, 25, 36, and 9. So I've just got a vector of numbers that I've assigned to the variable P. Now all of those numbers are positive. Now if I want to turn this into a probability distribution, all that I need to do is normalize it. And then again, remember, normalizing it just means that I'm dividing by the total value or the total area if I was talking about a continuous distribution. And I can do that with R by just looking at or finding the total value by just typing sum. So if I type sum, that tells me that if I add all of those numbers together, I get a value of 320. So I can turn this into a probability distribution by saying I wanted to assign P the value of what it originally was divided by the sum of what it originally was. So if I do that, then what is now in the variable P is a vector of values that are positive between 0 and 1, and if I sum over them, so if I sum P now, I do get a value of 1. So in this way, I can just make up a sequence of numbers. I can turn it, as long as the numbers are positive, I can turn that into a probability distribution just by normalizing it. So let's review our definition of random variables. So a random variable y is a function on our sample space into the set of real numbers. Now, our random variable y is said to be a discrete random variable if the image is either finite or countably infinite. The random variable is said to be continuous if it is not a discrete random variable. And just to review some of the notation, if we've got some real number little y, then when we write capital Y is equal to little y, we're really meaning the preimage of little y under the function capital Y. So that's really the set of elements in the sample space for which y of s is equal to y. Now this is going to be a subset of our sample space. If we have something more generally, if A is a subset of the sample space, then the notation y is equal to A really just means the preimage of the set A under the function y. Our CDFs and our PDFs for our random variables are defined as follows. So the cumulative distribution function, the CDF of a random variable y, is actually the probability that capital Y is less than or equal to little y. Now what that actually means is the probability of some subset of the sample space, so the set of S and S, such that the image of S under Y is less than or equal to little y. So if y is a continuous random variable, so in the continuous random variable case, then the probability density function, so the density function for y is actually the derivative of the cumulative distribution function with respect to little y. And in the discrete random variable case, then the probability density function for capital Y is actually given by the probability that capital Y is equal to some value little y. So all of this really just to remind us of our definition of expected value. So we've got naturally two cases, one for each type of variable. For the first case, if we let y be a discrete random variable, so in the discrete case, then the expected value of y is just going to be the sum over all possible values of y times the probability that y happens. So p is going to be the probability density function of y. Now again, in the case that this is an countably infinite set, then this will be an infinite series, and so we're assuming that the series converges absolutely. In the continuous random variable case, the expected value of y is actually given by the integral from minus infinity to infinity of y times, again, little f of y is going to be the probability density function. So we're really doing kind of a weighted average in each one of these cases. So a weighted average over the set of the probabilities for particular outcomes of our random variable. So now from our experiment, let's actually assign some random variables. So what I can do is I'm going to again assign a random variable y. And what do I want this random variable to be? Well, it's going to be a discrete random variable. I have this probability distribution p that I've just developed. And so let's say that I want my random variable to just be the positive integers 1 up to however long my vector is for my probability density function p. So I can do that in R by saying that y is going to be assigned the vector starting at 1 and going up to the length of the vector p. And so if I look at y, now y is going to be my values 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. So now y is my random variable that I've assigned in this situation. And so one of the nice features of R is that it has a sample function. Now let's take a look at what the sample function is. So I can go to the help screen. If I type question and sample, what it will give me is that the sample function, here's the description, takes an sample of a specified size from the elements of X using either sampling with replacement or without replacement. And so the arguments that we can hand the sample function, so X is actually going to be kind of the image values that I can have from my random variables, what I'm thinking about that as. So that's kind of my sample space or my image set of random values. The size is going to be the number of samples that I want to take. Do I want to sample from the distribution with replacement, or do I not want to sample with replacement? And then finally, prob is equal to, so prob is my value for my probability distribution that I want to use. So let's go back. And now we can say what is our, let's do a sample. So if we say y, little y is going to be the sample from capital Y of, let's say that we want 20 values, and I want to sample with replacement. So I want to take a sample, then assuming that the probability distribution doesn't change. And I want the probability distribution for sample to use is my probability density that I defined as P. So if I put that in, and then I type Y, so now R has sampled from my probability distribution P. It's done it 20 times, and if I look at the values of Y, I see these are the values that I can get. Alright, so let's review some of our numerical characterizations of our data. So if we're given a set of n measured responses, y1, y2, all the way up to y sub n, then we can define the sample mean of the set of n measured responses is really just what we think of as being the average. It is the average. Then we're going to add all of our values together, divide by the number of values that we have, and so we get our average. Now what that average really is what we call the sample mean. And the sample variance is kind of the average of the square of deviations of the measurements from their mean. So the sample standard deviation is actually defined as this computation. So what we would do initially to compute this, we would compute the sample mean. So from each one of our data points, we would then subtract the sample mean, square that value, add all of those values together, and then divide by n minus 1. Then the square root of that value is our sample standard deviation. And so these two values, the sample mean, sample variance, become very important when we're kind of characterizing some of our data. These are probably the two first numerical characterizations that we'll encounter. You might be looking at this wondering, well, okay, if it's an average, why am I not dividing by n instead of n minus 1? Well, there is a mathematical reason for that. We will get to that a little bit later once we start talking about things like biased estimators. So hold off that discussion. We'll get there in the future. So one thing that I can do in R is to have it do some comparisons for me. So little y was my sampled values that I had from this particular probability distribution. If I type something like y equal to 1, what R will do is to go through my vector of sampled values and just do a comparison. How many was the first entry a 1? Well, no, it wasn't. The first entry was a 4. Was the second entry a 1? No, the second entry was a 10, and it will tell me that's a false value. So I can get a vector of true-false values depending on whether or not that value in the vector was what I asked R to tell me if it was. So if I look at now 10, so if I would type y equal to 10 with a double equal sign, so that's telling R to ask a question, then I go through and say, yes, sure enough, I have a value of 10 in the second position, and I have a value of 10 out here in the fourth position, and then I've got a value of 10 pretty close to the end, so out here. And so no, R is telling me when and where I have those values of 10. Now R will treat trues as being 1 and false as being zeros. So if I wanted to know, well, how many 10s did I get, I can just say, well, let's sum y equal to 10. So I'm summing the values in that vector that it just did, and so I see that, oh, I have a value of 10 showed up 3 times in my sample. And so kind of doing this kind of check, I can see, well, is R actually sampling from the probability distribution that I wanted it to? Well, I'm going to increase values a little bit more so I can kind of get as many samples as I want. So let's go back and say that now I want to sample from Y. I want, so let's do 1,000 of them this time. I want to sample with replacement so that all of my samples are identical. And I still want to use my probability distribution P. So if I do that, R will now give me 1,000 samples. I've got a bunch of them in there. And so now we can do some counts. Okay, so how many times did I get a 1? Well, sum of y equal to 1. I got a 1 15 times out of 1,000. So if I look at the proportion of times that I actually get a 1, so sum y equal to 1 divided by the length of my sample, I see that sure enough, in 1,000 times, I have a percentage of 0.015. Well, if I look at the probability distribution, P, what is P of 1? P of 1 is in fact 0.015625. So the number of 1s that I get is fairly close to what my probability for 1 should be. Okay, what about my probability for 2? My probability for 2 is 0.009375. So if I look, well, how many times did 2 actually show up? What proportion of times did it show up? It showed up 0.01. So again, something fairly close to 0.009375. And if I can go through, I can go through and check all of the possible values from that. So how about the number of 3s? 0.034, probability of 3, 0.028. Okay, so a little further off, but what about 4s? 0.044, probability of 4, 0.0375. And so I'm seeing that yes, it does seem as though R is sampling from the probability distribution that I gave it. So here's a way of kind of running real-world simulations. Okay, so now remember that our expected value, so expected value was just going to be kind of this weighted average of over all possible values. Well, we can compute the expected value from our probability distribution because we know the truth, we know the actual probability distribution P that we developed. And so over the random variable y, if we in R just type y times P. Now what R will do with that is to multiply our vectors component-wise. And so we would take the first value, 1, times the probability of 1. Second value, 2 times our probability of 2. Our value of 3 times the probability of 3. 4 times the probability of 4, and so on and so on and so on. So R does a component-wise multiplication when I just do the multiplication symbol for two vectors. So now if I want the expected value, so expected value was that component-wise multiplication, so the value of y times the probability of y, and then I sum over all possible values. So if I sum y times p, I get a value of 6.88125. Okay, so that's my actual, honest-to-goodness, true expected value of y in this particular case. Well, come back to my samples. So I had 1,000 samples. How can I get that? Well, the sample mean is a way of getting at the expected value of y. And so how can I do the sample mean? Well, I can add together all the values that I have and then divide by the number of values that I have. So if I would sum over little y and then divide by the length of little y, that's going to give me a value of 6.845. But R, of course, gives me a shortcut function, and if I just type mean of y, it's going to do that same calculation for me. So it's going to add up all of those values, divide by the total number that I have, and I get a value of 6.845. Now, what was our true expected value for our random variable y? Remember, that was given by our summing together of our output values times our probability distribution, and that gave us an actual value of 6.88125. So here we can see that our samples, if we just do the mean of our samples, we end up with a value that's fairly close to what our true known value of our expected value will be for the random variable y. Now if we run another sample, we'll get different values. We'll get another approximate value for the mean. So we get, this sample mean we can think of as being the, it gives us an approximation for what our true probability distribution, what our true expected value is for our probability distribution. So often in life, in statistics, what happens is there is some known true probability distribution from which we are sampling. Now, we may not know exactly how to calculate that theoretically, but we are assuming that it is there. And we are getting at approximations to that known truth distribution by our experimental values. So we're going to experiment, we're going to take averages, we're going to find out about this probability distribution that we may not be able to calculate fully theoretically. And so that's the idea behind statistics in its relation to probability. So if we run a different sampling, so if we type y again we want to sample from capital Y. Again, let's do another 1,000 samples. We want to sample with replacement, and we want to use our known probability distribution P. So we get another sample. We can look at the mean of that sample. And here we get a value of 6.868. while our true value, our true expected value, is going to be 6.88125. So now, yeah, we're getting very, very good values that are close to that value. One could ask, well, if I increase the sample size more, am I going to get a little closer? Well, let's see. What if I make it 5,000? My mean for that sample, 0.68446. Again, my true value is 0.688125. So, not really. This kind of opens up the door to talking about estimators and whether or not an estimator is a biased estimator and what that means. We'll cover that in a later discussion. But basically, we don't want our estimators to really be dependent on our sample sizes for what we're getting. Okay, so more of that discussion later, but for now, let's continue our discussion of simulations and expected value with a discussion of roulette. So probably everyone is familiar with the game of roulette. Here we have a typical American roulette wheel. We've got numbers from 1 to 36 with an entry included for 0 and 00. Now as we would look at a roulette table, we're going to see a variety of outside bets that we can make. The table is laid out something like this. We've got our numbers 1 through 36, half of them in red and half of them in black. Then we've got our numbers 0 and 00. The variety of bets that we can make, we can either bet that we have that the ball, as it's spun around the roulette wheel, will land on one of the numbers 1 through 12. So that's betting on the first dozens. A second dozens bet, we can bet on the second dozens from 13 to 24, or the third dozens from 25 up to 36. We are also able to bet either the high or the low, so the low being 1 to 18, or the high being a number between 19 and 36. We can bet an even number, or we can bet an odd number, we can bet a red, or we can bet a black. If we would like, we could even bet a particular column that we have here, one of the three columns, first column, second column, or third column. Now, as we make these bets, we put our money down on the table, the ball is spun, and then we either win or lose. If we would make a red or black bet, the payout is really how much money that they would give you if you win for every dollar that you bet. So if I would bet $1 and I make the red or black bet, then they would pay me $1 if I were right. So the red or black pays $1, odd or even $1, high or low $1. Dozens will pay 2. So for every dollar that I bet, I could win $2. Same thing for the columns. For every dollar that I bet, I could win $2. Now, something to notice here is in this table is something called house edge, and that's actually given as a percent. So the house edge, remember that house edge value for all of these bets as 5.26%. Let's see where that actually comes up in our discussion. So let's let the random variable d be an experiment in which we are making a dozens bet. Now, each entry on the roulette wheel is going to be equally likely, and so we've got values for n of being 00, 0, or 1 up to 36. So that gives us a total of 38 possible outcomes, a uniform probability on that, then gives us a probability density of 1 over 38 for each one of those outcomes. Now, our random variable d is going to be a map from our sample space to the values of -1 or 2. Now, what those values actually represent are really our payouts. So if we would place our bet, if we lose, then we lose our dollar that we put down. If we win our bet, then we would actually take away $2. So those are possible values that we have for our random variable D. So now the probability that D will actually be 2, so the probability that we win $2, we've got to get one of the 12 possible values. And so for one of those 12 possible values, we've got 12 over 38 for actually winning. The probability of losing is going to be the complement of that, so 1 minus 12 over 38 gives us 26 over 38. Computing the expected value for this, so the expected value of D, we have the value of D times the probability, so so our value of $2 times our probability of winning $2 plus our losing $1 times our probability of losing $1. Now if we make that calculation, we end up with a value of -1/19. Now that -1/19, if we look at the decimal expansion of that, lo and behold, we get 0.0526. Now that should look familiar from the previous slide. As a percent, that would give us 5.26. In the previous slide, that was referred to as the house advantage. So what that really means is that in the long run, the expected value, so if we play this over and over and over and over, do several simulations, what's likely to happen? We are likely to end up in the hole by about 5 cents, about 5 cents for every dollar that we would actually bet. So let's see how this would actually play out in our simulations. So that's referred to as the house advantage because the house always has the advantage, and it will take your money. So bottom line, don't go into any gambling casinos, y'all. Alright, so now let's fire up R and do some simulations of our dozens bet. If we get R started, so let's begin by looking at our probability distribution. So our probability distribution for our dozens bet was, so if we would lose, then our probability of losing was 26 over 38. Our probability of winning, on the other hand, was just 12 over 38. And so if we look at our probabilities, there we have them. Let's check just to be sure that those actually sum to 1, and sure enough they do. So now the range for our random variable. So we've got a random variable D that we said took values of either -1, so if we were going to lose our dollar, or what it would pay out would be 2-to-1, so we could gain $2 for every time that we actually win. So our random variable D is there a vector with a value of -2 or 1. Computing the expected value, so we computed it experimentally just a second ago, or we did it theoretically just a second ago. We can compute that again in R, that if we do the sum of D times P, sure enough, we have a house advantage of -0.0526. So the house is likely to win about every 5 cents of every dollar that we bet. Okay, so now let's run some simulations to see what happens. Okay. Kind of looking things up on the internet just to see, we can get on average about 59 spins per hour for a roulette wheel. Now that depends on the number of players, of course, and things, and you can confirm that number. But let's just take that we get about 59 spins per hour, and we go in a casino. Say we're there for 4 hours. Let's see what happens. So in 4 hours, at 59 spins per hour, we're looking at 236 spins. So let's say that's our number n. And whoops, 59. So for our casino, for the night that we will spend at the roulette wheel, the 4 hours that we will spend will probably have 236 plays there. So let's see what happens. All right, so in our simulation, so our winning and losing, so let's say that we have little d. We want to sample from big D, so our random variable D. We want to do it n times, so n was our 236 times in our 4 hours at the casino. We want to sample with replacement because we want each game to be independent of all of the other games. So we want to sample with replacement, and our probability distribution is P. So let's see what happens at our first night in the casino. Well, if we hit D, we get a bunch of values of either -2 or 1s in different spots. And so let's see what happens. So in that 236 spins, we're imagining that we're betting $1 for each time. So let's see what our results are if we add all of those things together. Sometimes we win, sometimes we lose. So our sum of our night in the casino, wow, we are in the hole after that first night, a total of $11. So we would walk out of that casino with $11 taken out of our bank account. So we lost money on that night. Okay, so sure enough, well, let's see how this would play out with our expected value. So our expected value, mu, was our sum of D times P. So our expected value, we would lose by about 5 cents. So if we end up spending $236, so that's our bet, what happens? So if we do n times mu, how much would we expect to be in the hole? Well, we'd expect to be in the hole about $12.42 in our 236 bets. Pretty interesting. So we simulate this, and sure enough, we end up in the hole about $11. Okay, well, maybe the next night at the casino will be better. So let's see what happens. So if we simulate another run, so we go again, 236 spins, we get D. Let's see how much we walk away with on this one. Wow, we're down in the hole, $23 this time. So we've gone to the casino, we've spent 8 hours in the casino, and we have lost now $236 more than one time, and now we're even in the hole again tonight by $23. So this really isn't boding well. Do you kind of see how casinos stay in business? That slight advantage, that negative expected value, it's not much of an expected value. It's only slightly negative, 5 cents on every dollar, but 5 cents on every dollar times the number of dollars that you spend, that's how they can afford those huge, awesome, amazing buildings. They will take your money mathematically. They will take your money. And so what happens if we go a third night? Again, we're in the hole, $11, 26, 20, 8. We had a good night there. We only lost $8. Ooh, that was a bad night. $59 in the hole. $29 in the hole. Hey, finally, after all of those nights, we get a really good night and we are up $19. So, finally, after however many nights, 1, 2, 3, 4, 5, 6, 7, 8, 9 nights, we end up finally having a winning night. So it's not impossible for us to come out a winner, but what expected value actually tells you is in the long run, here's what is going to happen. Okay, so in the end, if you look at the average over a long period of time, we will end up in the hole. It's probably not too hard to see that that's going to be the case in each one of these situations. One night we may be positive, but in the long run the casino will win because the odds are in their favor. Now, another thing that we might be interested in that this kind of opens the door to is, okay, so we know that we're going to be in the hole. A question that you can ask would be, so if I'm going into the casino, I'm planning on betting $236, and I know I'm probably going to lose a little bit more than that, how much extra am I going to lose on average? Okay, so what's the most likely biggest deficit that I could run? I mean, we saw this time I lost $59 one night. 11, 26, 20. So one thing that we can say is how big is the spread in our losses that we will actually use? So how much extra do we need to bring the casino on average before we are totally tapped out and we have no money whatsoever left? Well, that is the question that's answered by another numerical calculation, and that numerical calculation is called variance. So we saw that again just previously in this video. We're talking about variance and standard deviation. So what is the spread in our data? So now let's do a little scripting to demonstrate variance whenever it comes to sampling. So let's start our favorite text editor, and let's call our script simulation.r. So mine is Vim, so now let's go through some of the commands that we'll do to simulate our bets with roulette. So let's start off by clearing the workspace so we're sure that we don't have any other variables lying around. Workspace. So I'll put that comment there, so we'll kind of comment our code as we're going along. So the command to clear our workspace is rm, so remove, list all the variables in the workspace and clear them. So in our simulation, we had the probability for our dozens bet. Our probability of losing was going to be 26 over 38, and our probability of winning the bet was 12 over 38. Our payoff, so our values for each one of the variables, our payoff for losing, we would lose $1, and for every time that we would win $2. Okay, so this was our probability for the bet, and this was our payoff for the bet. Now we are able to calculate the expected value. So our expected value, mu, in this particular case was going to be the sum of our probability distribution times our payoff, and our variance was going to be, so using a formula from one of our previous videos, if we do the sum of the expected value of d squared minus the expected value of d, squared, then that would give us our variance. So now our standard deviation, sigma, was then going to be the square root of our variance. Okay. So now we wanted to simulate going to our casino several times or seeing several rounds. So our number of rounds that we would see for every night that we would go to place our bets, we were assuming that we would see about 59 spins per hour, and that we would be there for 4 hours at a time. Then we want to save our results of how much we win or lose in a particular night. So let's declare a variable, results, and we'll just declare that variable. We won't tell R necessarily what it is yet. We want to tell it to make room for it. So it will take care of the memory allocation as we go. And then how many days do we want to go to the casino? Well, we can do a for loop, and let's days be in the range from 1 to 365 days. So let's say that we spend an entire year in the casino placing this bet for 4 hours a day. This is what we're doing. So our sampling, our results, we would sample from D, our payoffs for a total of n times. We were sampling with replacement, and we were using the probability distribution associated with our dozens bet. Then the results, so the results for a particular days, that was going to be the sum of so the net of our payoffs, so our losses and our gains for a particular day's worth of gambling. And so this is our script, so we'll simulate it for 365 days, playing for 4 hours a day. Let's run the script and see what our results are. So now let's get R started. So we have R started, we have our script, and we want to run that script. So we do that by sourcing our code, and our script was called simulation.r. So we ran the script. It ran without any problems. We didn't have any error messages, and if we look and see what variables are now in our workspace, we see our variables from our script. We had D was our samples, big D was our sample space, the image of our random variable, our variable days that counted the days that we were in the casino, our expected value. So all of our things are there. Let's check mu. That was our expected value. So we expected to lose, on average, a single bet. We would lose 5 cents for every dollar that we actually bet. And so if we look at our results, so our results, we had 365 of them. So what this shows is that on the first day, we actually had a gain of $4. Second day, we lost 20. Third day, we lost 23. Fourth day, we lost 23. Fifth day, we lost 8. And so if we look at kind of the average amount that we lost, so the average that we lost, so if we do mean of our results, on average we lost about $13.82. How much would we expect to lose in this particular case? Well, doing n times mu, we would expect to lose $12.42. So on average, we would expect to be down $12.40. We were actually down on average $13. So a little worse than what we would expect to have happened, but still kind of in the ballpark. So now we wanted to get an idea of the spread of our losses. So now comes the sample variance. So what did we have for the variance? So the variance on one particular round could vary by 1.944. So in our number of samples, so in seeing things a total of 236 times, we would have a variance of about 458 if we actually calculate the variance of our results. We see that again we get a number that's fairly close to our variance. We have a variance of 458.92 is what we might expect, and our actual results running this experiment for an entire year, we end up with a variance of 450. And so our actual standard deviation of our results would be about 21. And what we have then as the square root of n times our variance, again pretty close, 21.42254. Okay. So now the standard deviation of our results was going to be 21.22007. So that's giving us a measure of the spread of our data. So if we look at our average value, so if we look at the mean of our results, so the mean of our results plus the standard deviation of our results, then that gives us a value of 7.3926. If we go one standard deviation below our mean, so if we look at the mean of our results minus a standard deviation of the results, now we're down to about minus 35. So if we count now the number of times that we are in between negative 35 and 7, probably we're going to get somewhere around 66% of the time. Let's do the calculation and see if that's about right. So if we sum the results that are greater than negative 35 and we want our results to be less than 7.39. So if we look at that, then we have 235 of them. So of that 235, what proportion of them? So if we divide by the length of our results, then we end up with about 64% of our results being within one standard deviation. Number of results typically within 2 standard deviations of our mean will be about 90%. So let's see if we go 2 standard deviations. So if we go mean of the results minus 2 times standard deviation of results and mean of the results plus 2 times standard deviation of the results. And there we get about 97% of the time. So usually about 97%, 98% of the time, that's going to be within 2 standard deviations. And so we see that consistently here in this particular case. So the standard deviation actually gives you a measure of the spread of your data, and we can actually see that in this particular case. So hopefully this gives you a little bit of insight. This is a little bit of sampling. We just kind of touched on the surface of the statistics part of this course. So more about that later, much more about that later. Hope you all enjoyed this, and see you next time.